Hello, and thank you for watching our project presentation. Our project is called the Quantum Reservoir Computing for Swaption Pricing and Forecasting. I'm participating in the track 2 of the quantum machine learning of Qiskit Fest in collaboration with Quandela. So in this talk, I will show you how we apply hybrid quantum model to predict swaption prices and how our quantum approach improves over a classical baseline. So, myself Virat, and I'm the only one in the team. And so, let's get started. I would first like to thank all the sponsors for making this hackathon and Fall Fest possible. I would like to thank University of Paris Saclay, Unitary Foundations, Quandela, Alice and Bob, Acora, Atropica Labs, IBM Quantum for organizing this amazing fest. So, what is swaption? A swaption is an option on an interest rate swap. It gives the holder the right but not the obligation to enter a swap at a future date. Swaptions are widely used to hedge interest rate risk and to structure complex fixed income products. Their prices are highly nonlinear and depend on multiple factors such as time to maturity, tenor, and market conditions. This makes them an interesting and challenging target for our quantum machine learning. So, Our goal is to learn a function that maps tenor, maturity, and time to corresponding exception price. We focus on quantum machine learning to capture the non-linear structure of the pricing surface and to forecast future prices. A key requirement of the challenge is to compare a quantum model against a classical benchmark. So we designed three models: a purely classical baseline, a purely quantum reservoir model, and a hybrid model that combines the both. Dataset. The dataset is provided as simulated subscription price grids where each cell corresponds to a specific tenor. We convert this into a log format dataset. To prepare the data for modeling, we encode the data as an ordinal value to capture time progression, and we scale all features into the range between 0 and 1. Sorry, to 0 and 1. This format works well with both classical and quantum models. So, for the classical baseline, we use ridge regression trained on the scale, features, maturity, tenure, and time. Ridge is a good benchmark because it is simple, stable, and interpretable, and it does not overfit easily. On our evaluation subset, the classical ridge model achieves a root score of squared root mean squared error of 0.597, and an absolute error of 0.0492. These numbers give us a reference point to judge whether the quantum model actually adds a value. Our quantum reservoir concept. So our quantum model is based on the quantum reservoir computing. The idea is to use a fixed quantum circuit as a non-linear feature map. We encode each data point into qubit rotations, apply a random entangling circuit called the reservoir, and then measure Poly-Z expectations from each qubit. These expectations from values from a quantum quantum feature vector, and we train a classical ridge regression as a readout. Importantly, do not backpropagate gradients through the quantum circuit, which makes the approach more stable on near-term hardware. In our implementation, we use three qubits, one for each feature, maturity, tenor, and time. Each feature is embedded with the rotation gate Ry pi times the scaled value. We then apply an efficient SU2 circuit with the depth of 2 and pairwise entanglement as our reservoir. For measurements, we compute the expectation value of the Poly-Z operator on each qubit using Qiskit AER's estimator primitive. These three expectations value form our quantum feature vector and a ridge regression readout from scikit-learn. maps them to predict the price. Then the training strategy and scalability. Running a full quantum simulation on more than 100,000 data points would be very slow. With the current simulators and hardware to make the solution practical, we train the evaluate the quantum reservoir on a representative subset. This allows us to compare the quantum and classical models fairly. For the full-scale forecasting, we use the classical ridge model, which is a computationally efficient. This is hybrid strategy, reflects how quantum will likely be used in the industry, quantum for feature discovery and benchmarking, and classical for the large-scale inference. And lastly, our results. This table summarizes our main quantitative results on the evaluation subset. The classical ridge model has an RMSE, means root mean square error of 0.0597 and an mean absolute error of 0.0492. The quantum reservoir had RMSE of 0.057 and MAE of 0.0455. The best results are achieved by the hybrid model, which concatenates classical and quantum features and then trains a ridge regression. The hybrid model reaches an RMSE of 0.0451 and an MAE of 0.0373, which is significantly lower than the classical baseline. This demonstrates the quantum generated feature provide the additional predictive power beyond the classical feature alone. So to conclude, we demonstrated that a quantum reservoir model can outperform a classical ridge baseline for swaption price forecasting. A hybrid model that combines the classical and quantum features achieves the best performance overall, and our approach is technically sound, mindful of hardware realities, and direct applicable to real financial problems. So, thank you very much for your attention.